So first off, thank you all for coming. Thank you to JuliaCon for giving me the opportunity to speak. What I'm going to talk about today are two packages in particular that make up a different kind of financial simulation, right? So this is going to be a baseline implementation of an agent-based financial simulation. What I've been working on as part of my PhD thesis, right? Packages are listed there. So typically when people will think of like financial modeling, they'll think of two different approaches, like we can say market replay or these top-down forecasting methods, right? So both of these will rely on historical data sets, which can be expensive, finite, and static in the sense that, it is what it is, what happened, right? So with backtesting, right, we're going to wind back the clock, and we could send in a model just to see how it would have performed if it would have been there at that, point in time. And so these can be quite sophisticated and, work quite well. One thing which can maybe be a downside is that they're unresponsive. So if you, there's no reaction to your action, that feedback is not present in something which is only using historical data sets. There's no divergence from price history. And moving on to forecasting, these top-down methods, have been around for a long time. Can be like very famous, and they'll essentially condense these very complicated things like price series into a small amount of parameters, which we can then fit to historical data and then use to generate these synthetic time series. And one thing that these can struggle to do sometimes is model these financial contagion effects. So effects in like a big network of things and how maybe things can interplay there, or emergent phenomena. So things that can manifest unexpectedly, things like the flash crash of other market crashes. Ideally, we would want something that maybe can sort of abstract this idea of time here and capture the statistical properties of these financial time series. And rather than maybe here try to focus on prediction, I want to focus on representing these financial time series as best we can, so that we can then turn around and go and interact with something. So having a feedback effect for the actions taken in this simulated environment. We want to be able to tune it so we can generate data for things that we don't, either we have only rare instances of in history, or maybe for things that we don't have any examples of in historical data. And so the ability to generate these what-if scenarios. So let's say if we wanted to generate 1,000 different market crashes, and then maybe see if we can train something, an algorithm to be robust against that. Or if I'm a policymaker and I want to change some sort of market rule and I want to generate data for what the effects of that could be at the aggregate, right? We want something that's expressive, something that can generate these really complicated and nonlinear effects that we do observe in these really emergent properties, right? So this is the vision. This is not yet the reality. What I'm going to talk about today is our progress toward this goal, how Julia fits into that, some preliminary results, and then some next steps. A little background. So real markets operate through order books. They can be thought of as this representation of supply and demand, two-sided. Buyers submit bids, sellers submit asks. Bid price is the highest price a buyer is willing to pay. Ask price, the lowest price a seller is willing to give up their asset for. And if you're patient, submit your bid here in this queue and then wait for things to sort of shift your way through a limit order, right? This sort of pending order in the queue. If you're impatient, you can go and just immediately execute this. So seller goes and acquires things at the bid price, buyer similarly at the ask. And all of this will occur at a snapshot in time. And then as this evolves, we get these several various states, and the price emerges from this. And this is what we model. We model the interactions at the micro scale. So the actions behind the orders, they're being submitted here in the book. And we're almost hoping that these, the properties we really care about, like the price, et cetera, just emerge as a byproduct at the macro scale. To do so, we use agent-based modeling. So this has three separate components, the first being software agents. These are autonomous agents that are heterogeneous, right? They can be defined with different properties and exhibit fundamentally different behaviors. The interaction includes the available actions made to these agents, as well as the explicit structure to which they are linked. The environment defines the state of the system. This includes the observation space, observable variables, things like external shocks to the system, things that can be like news propagation, right? A little more nuance can be the representation of time. Do we look at time as a discrete sort of trading round where you can see everything that happened before it gets to your turn? Or do we think of this more as how it is in reality, where it's continuous and decisions are being made in parallel? Two additional steps to generate realistic phenomena. We rely on both calibration and validation procedures. Calibration occurs before running the model. It's where we sort of determine these parameters to then get these models to generate realistic phenomena. These can be calibrated through heuristic methods, or if you've got it, historical data. After you've run this model, to then trust these results and make sure that this is something you can depend on, we can run a series of tests. In the literature, this is known as stylized facts. They're essentially these statistical regularities that have occurred, and they've been studied for a long time, really a subject in and of themselves. And we'll look at these as like a test set and say, okay, if we can achieve all of these, then we can now have like this sort of abstract, generalized, fidelity test, right? So we're able to then, guarantee that, or I shouldn't say guarantee, but able to have more trust in our sort of what-if scenario where there's no ground truth. We can say, okay, well, there is some sort of built-in trust that we can have here through this validation procedure. How we implement this in the Julia leverages several existing packages. Our two main ones are that we're going to talk about here are these trading agents. These are the actual agents that we making these decisions. And the brokerage.jl is the sort of how we've implemented this as like a server that is going to process all these orders. The agents make decisions in parallel. The orders are processed serially. Within brokerage.jl, how this is implemented right now is we'll spin up a remote server using http.jl. It's going to route these internally to these various different microservices. There's this API interface that the agents will then connect to, right? And then these orders will be routed to their respective location. Could be a relational database so that we can have a large number of agents, or they can be processed through these order books. We've implemented in-house a package that essentially reproduces these matching algorithms. It's been validated against empirical data, et cetera. And then they'll also query things like the observable market information. So the agents themselves, we're going to sort of take a minimal assumption approach here, right? Because it's a baseline. We're going to think of the first type as these liquidity providers. So these are going to draw randomly a limit price to normal distribution, depending on the market state as well as their agent state, as aka their inventory and cash. They're going to take an action and add these orders to this level of the book. They're going to be the primary source of price movement resistance. Liquidity takers similarly will determine a random amount of their wealth to put up to risk and then randomly set these portfolio weights. Similarly, they'll take price away. They're the primary movers of price movement. They only do market orders. Liquidity providers only submit limit orders. A little more specific is the market makers. So they're going to determine a random spot within this sort of price levels to submit this limit order and concurrently place them. If they have an inventory, sometimes they'll also hedge. Also, all of this is done randomly. We did design one intelligent agent. We read in the literature that just using these sort of simple zero intelligence, they call them behaviors, a lot of times you'll observe like price instability. And so this is added just for the sake of wanting to have less unrealistically volatile behaviors, and we're able to see that just by introducing this intelligent agent. This agent uses these handcrafted optimization procedures. I just used JP Morgan AI research. They had some sort of a implementation. We made our own version of that with online machine learning so it could function on the fly. And essentially how they work is a three-step decision policy. This is implemented through convex.jl for the optimization procedures, which I could make convex, and then jump for the optimization procedures, which I could not. And so this simulation can run without the intelligent agent, but we do have it there for the sake of completeness and stability. So how this will work is, as an example, we'll spin up a server, initialize these agent parameters, and then generate this price and volume data. And then over time, we're going to notice these actions come together and generate these macroscopic properties at the aggregate. So in line with wanting to make minimal assumptions on these initial agent behaviors, there's minimal parameters. We're going to look at the number of agents, instantiate their cache and inventory range. They'll be allotted something within here, once again, randomly, and then they'll have a trading frequency. And then as for the market, we just set the market hours, number of assets, etc. In terms of performance, we've been able to scale this up just because of the fact that everything is distributed, right? And so as the first sort of a proof of concept, we started with just one asset, 142 agents, moved on to something which these parameters were derived a little bit from. They're loosely based on some studies in the high frequency literature. And then we've just scaled it up to 30 assets and over 100,000 agents. All this was done with very modest research equipment, my desktop in the office, right? And then when my lab mate wasn't there, his desktop in the office, right? And so, I think with minimal optimization in terms of like getting, I do what I can, right? But I'm sure that this could, perform a lot more with more time and effort. So let's talk about the validation, these stylized facts. So all these facts will run across 10 different trials of the synthetic price series, and all the results are consistent across these 10 trials. A lot of these stylized facts will take as an input a return series. Returns, we can just think of maybe as normalizing the data in a sense, and pretty simple, right? Just return of investment, the gains and losses investment generates over a period of time. The first one I want to look at is the non-Gaussian characteristic of returns distribution. This matters because extreme events occur more often than one would normally expect. And this is first mentioned in the literature some time ago. I've re-implemented this with some recent data, just to ensure that it's still there, as well as our tests are working as they should and not wanting to get any false positives. I've included as a comparison maybe something we've gotten from a traditional model, something like geometric Brownian motion, which is then fitted to the Apple data in the top right, and then what our simulation would get when it's removed from any sort of empirical data. We did not use any empirical data when generating these simulations. It's all from first principles in terms of representing the market as best we can, including these order types, the matching algorithms, order books, and then assuming just noise, essentially, for the actions taken here. And apparently this was enough to generate the, at least, heavy tail returns distribution, right? Something else is the linear unpredictability of return time series. Once again, shown in the literature, why this would be important is that knowledge of past events cannot help predict future movements. Big movement today doesn't necessarily imply a big one tomorrow, right? Once again, verified with empirical data, contrasted with geometric Brownian motion, and then our simulation. Something that's a little interesting here is that this test doesn't necessarily hold for extremely short lags, right? So it's a byproduct of just microstructural effects. That bid-ask bounce is gonna make it seem like there is some sort of negative correlation. A buy now, a little more likely to be a sell later, right? That's what we observe, and something that I also see in our simulation versus non-geometric Brownian motion. Nonlinear dependence is where there's significant positive autocorrelation or a persistence and volatility of returns. A big price movement today, or very volatile day is going to be followed most likely by another high volatility event, versus low volatility events are probably going to be followed by another low volatility event. Something observed in literature, verified empirically, Apple returns for various nonlinear functions, not seen in geometric Brownian motion, and observed in our case for just our baseline implementation. Last one I'm going to show, gain-loss asymmetry. This is it's an inverse statistic, essentially the distribution of first passage times. So the time it takes to hit a fixed return level. Normally we'll see more likely that, there's an asymmetry here. So normally it's faster to lose money than it is to gain money. And something that's seen literature empirically, not as much, and something that we are, at least we think, able to capture. We're going to need more analysis here and then fitting a maximum likelihood fit to the actual curves to get a better idea of, are we getting any asymmetry? But at least for now, we can say, at least for capturing the properties, better than geometric bounding in motion. Things that we don't get are things like stylized facts that are related to volume. None of our agent behaviors are even conditioned on volume, so we're not too surprised there. There's also effects that we see that are related maybe to historical price trends. Once again, our agents are not conditioned on any sort of price history. I'm not surprised we don't get those either. But if anything, we're able to sort of use this information to say, okay, maybe now we can think of things that we know we need to add in order to eventually hope to get the full spectrum of these stylized facts, of which there are many, and which we are still in development of, the test cases, and the like. To summarize, the detailed elements of the market structure, things like the order books, decisions being made in parallel, are important to modeling these financial time series, right? So accounting for these elements were needed to capture these complex behavior at the aggregate with just simple behaviors at the micro scale, right? So the simple all coming together to make this complexity emerge, right? So the intelligent agents, they did improve stability, but their inclusion did not necessarily provide any new stylized facts. This was a little interesting because the strategic behavior didn't necessarily provide any new statistical regularities. And so this made us think that, okay, maybe conditioning on the right observations, adding things to the observation space, like this information propagation, things like historical trends, these different shocks are probably more necessary than there is in perfectly replicating human behavior, which should also be a good thing because it's probably easier to do that than would even attempt to try to model human behavior, right? So components of brokerage.jl will need to be isolated and optimized further if we want to continue to scale this. Right now, just as a baseline implementation, all the order books are stored in one place and they're stored in the same place as I keep the database. So big bottleneck when it comes to processing these orders, limits the amount of transactions we're able to scale to, and the like. So I guess we would like to isolate these, maybe keep if anything, this gives an opportunity to try and model, like in real life, the fragmented exchange systems. So your orders can be routed to various exchanges. There's even things about off-exchange trading. So the ability to maybe come in here and further optimize this simulation environment to include things like that, right? So lastly, the high performance and data science capabilities of Julia have already and will continue to help improve the performance of our agent-based platform. The next steps will include leveraging Julia to process these large data sets. Right now, there's another bottleneck when we scale up number of agents, then the search for sort of agent, when they query this database, there's another bottleneck when it comes to searching this ever-growing database. And we could look into different ways to process that, maybe look at a different database architecture, or even maybe sort of make multiple brokerages, who knows. As well as wanting to generate more sophisticated agent behaviors. It's a well-known problem that the financial data is anonymized. You don't know where an order came from. And so that makes it really difficult to try and fit any sort of machine learning to learn an agent behavior. Alternatively, we could, some people have viewed maybe we just have one agent, which is just the world agent, right? And so you're interacting with this one agent, which has been trained across a whole, bunch of order book data, and then having that rely on like the whole interaction and things like that. And so we've recently been able to obtain historical data, and these are some of the things that we're looking into as some next steps. Lastly, I'd like to acknowledge my advisor, my lab mates, Polygon.io, for providing the data, which a lot of this would not be possible without. And thank you all for coming and your interest. Thank you.
Do we have any questions?
Those are actually super cool, because I'm a financial economist, and I do a lot of my work on market microstructure, so this is kind of fun to see. One of the things that I noticed in particular that feels very weird is like how flat the prices look.
Yeah.
Your volatility is more or less constant, which is like conditional stochasticity, meaning like volatility changes over time. As these big spikes can kind of drive that. And there's a lot of interesting ways you can do that. And the fact that you have a lot of you have the ability to add heterogeneous agents, basically means you can get to ridiculously complicated. Like capture just a lot of stuff. So one of the big ones would be institutional trading. Like people who show up and just every once in a while they just drop these huge orders in, either on a small bit by bit basis, dividing up the order and just trading every 5 minutes, same quantity. That's one way you could introduce a lot of stuff. And I missed the first part of the talk, but are you do you have the price sequence, the underlying volatile value? Is that motion? That's all determined by
it's all determined by the agents. I have seen people do that though. Goal was to, like I said, minimize the amount of stuff we add in. Right, the whole idea of Occam's razor. Some of us try to do the best, and then maybe we build from there. So there is no fundamental or underlying value. It's all I do instantiate an initial price, but that's it.
Yeah. Okay. Cool.
But yeah.
I have some other comments, but I'll
How do you handle assets leaving the market? So if the value of the asset is effectively random, what happens when it reaches a near zero value?
So the question is, how do you handle assets leaving the market, specifically when the asset is leaving the market, the value is close to zero?
Yes, that's something we've really even gotten to the point where we're thinking about that yet, right? So we haven't really seen that yet, because if anything, I guess instinctually I just set it high to minimize that wrapping, right? But no, there's a lot of things too, where let's say something like a delisting event or bankruptcy of this company, whatever, something that will cause it to crash dramatically. I imagine some things like that would have to be added as an external news thing that would cause it, right? And then we would have to allow for it to reach zero, right? Right now, I might even have it as I throw an error, right? But there's a lot to think about here, right? But yeah, no, thank you.
Any other questions? All right. If none, let's thank the speaker again, and we'll set up next session.